Hello everyone, welcome to the channel V2 Electronics. This video is about a common collector configuration. Common collector configuration is the third and final transistor configuration in the BJT configuration. This is a symbol of transistor where the collector terminal is common for both input and the output. That is, it is common for base and the emitter terminal. Here we can see the common collector configuration with the proper current directions and voltage notation. This common collector configuration is used primarily for impedance matching purposes since it has a high input impedance and low output impedance, which is opposite to that of the common base and the common emitter configuration. Here NPN transistor is taken as an example with a common collector, and proper biasing is applied to the NPN transistor and respective current directions are shown. Along with this, the common collector configuration which is provided with the load resistor is considered. That is, the resistor is connected from emitter to ground. We can also notice that the collector is tied to the ground even though the transistor is connected in a manner similar to the common emitter configuration. For all practical purposes, the output characteristics of this common collector configuration which is same as the common emitter configuration. For the common collector configuration, the output characteristics we are going to take IE versus VCE and for a range of values of IB. And the input current therefore is also same for both common emitter and the common collector characteristics. Therefore, I am not going to consider the input and output characteristics of this common collector configuration in this video. Therefore, the sign, if we change the sign of the collector to emitter voltage in the common emitter characteristics, we are going to obtain the common collector configuration. Almost unnoticeable change in the vertical scale of IC of the common emitter characteristics if IE is replaced by IC for common collector characteristics. For the input circuit of the common collector configuration, the common emitter base characteristics are sufficient for obtaining the required information. Next, I am going to consider one more topic with this common collector configuration, that is analysis or design of a transistor amplifier. The analysis or design of a transistor amplifier requires knowledge of both the DC and the AC response of the system. The transistor can raise the level of the applied AC input without the assistance of any external energy source. In actuality, any increase in AC voltage, current or power is the result of the transfer of energy from the applied DC supplies. So this analysis or design of any electronic amplifier therefore has two components, a DC and an AC portion. During the design or synthesis stage, the choice of parameter for the required DC level will affect the AC response and vice versa. The DC level of operation of a transistor is controlled by a number of factors including the range of possible operating points on the device characteristics. Once the desired DC current and voltage levels have been defined, a network must be constructed that will establish the desired operating point. So next we'll consider what is that operating point. For a transistor amplifiers, the resulting DC current and voltage establish an operating point on the characteristics that define the region that will be employed for amplification of the applied signal. because the operating point is a fixed point on the characteristics. So it is called as a quiescent point, or simply we can say Q point. By definition, this quiescent means quiet, still, inactive. In this figure, we can see the general output device characteristic with 4 operating points indicated, that is A, B, C and D. The biasing circuit can be designed to set the device operation at any of these points or others within the active region. Here the maximum ratings are indicated on this characteristics by horizontal line for the maximum collector current IC max, and vertical line at the maximum collector to emitter voltage, that is VCE max. The maximum power constraint is defined by this curve, that is PC max in this figure, and at this lower end of the scales are the cutoff region, which is defined by IB, which is less than or equal to 0 milliamps, and the saturation region, which is VCE, which is less than or equal to VCE sat. Now we shall discuss the various points one by one. So if no bias was used, the device would initially be completely off, resulting in a Q point at A. Zero current through the device and also zero voltage across it, because it is necessary to apply a voltage or biasing a device so that it can respond to the entire range of an input signal. So this point A would not be suitable. For point B, if a signal is applied to the circuit, the device will vary in the current and voltage from the operating point, allowing the device to react, and also sometimes it is possible to amplify both the positive and negative excursions of the input signal. If the input signal is properly chosen, the voltage and the current of the device will vary, but not enough to drive the device into cutoff or saturation. Next is a point C. This point C would allow some positive and negative variations of the output signal, but the peak to peak value would be limited by the approximity, that is VCE, which is equal to 0 volts, and this IC, which is equal to 0 milliamps. Operating at this point C also raises some concerns about the non-linearities introduced by the factor that the spacing between the IC curves is rapidly changing in this region. Next is a point D, which sets the device operating point near the maximum voltage and power level. The output voltage swing in the positive direction is thus limited if the maximum voltage is not to be exceeded. In general, we can say it is preferable to operate where the gain of the device is fairly constant, or we can say linear, to ensure the amplification over the entire swing of input signal is the same. So the point B is the region of more linear spacing and therefore more linear operation, and therefore it seems the largest possible voltage and current swing. Next point we need to consider is the effect of the temperature. So having a selected and the biased BJT at desired operating point, we must also take the effect of the temperature into account. Temperature causes the device parameters such as the transistor current gain, that is beta AC, and also the transistor leakage current ICEO, which I have already explained in the common base characteristics and common emitter configuration. to change. Higher temperature result in increase in this leakage current on the device, thereby changing the operating condition set by biasing the network. The result is that the network design must also provide a degree of temperature that stability so that the temperature changes result in minimum changes in the operating point. And this is about a common collector configuration along with the analysis or design of an transistor amplifier. Thank you.